Hello and welcome back. Last lecture we were looking at the quantization of nonabelian gauge theory. So quantization is a way of guessing a quantum system that has the symmetries that you want. And in the last lecture, we started the process of understanding which quantum theories we can guess using the path integral prescription for an non-abelian gauge theory. And we went through some derivations. We started with a path integral prescription where we integrate over the fermions and the gauge bosons. We noticed that gauge equivalent configurations of this gauge field A will give exactly the same contribution to the integrals and that would lead to naive divergences. And then we fixed the gauge, so we dealt with this overcounting. We dealt with the overcounting by fixing the gauge, which is another way of saying we picked one representative from every equivalence class of connection fields, where the equivalence classes are determined by gauge equivalence. And then we did that in essentially the most naive way imaginable. We just put in a delta function inside the path integral here to select out just that one representative from each gauge orbit. There were some subtleties about how you selected the representative, which I discussed, but we're largely going to ignore those for this course. And then we got something nonlinear. Because it had a Jacobian inside the path integral. There was this debt of this functional integral. And then the genius insight that allowed us to get further was that determinants they can be computed by introducing auxiliary fermion fields. C of x, and these are ghosts. So after all these steps, we end up with the transition amplitude that's computed by the path integral here. The prescription is instead of, this is just the guess, right? We guessed that we could compute transition amplitudes by path integrals. We immediately saw problems, we dealt with the problems, and now we feel that we've dealt with them all. We confident enough that we could define this transition amplitude by a path integral no longer over just the a's, but also over the psi's and over these ghost fields, C and C bar. And after all these manipulations, especially after this particularly cunning step here, we can see that we can write that path integral as in e to the is form. So the main roadblock for doing that from the outset was this part here, right? We had this, when we put the delta function into the path integral to stop it overcounting, we ended up with some horrible nonlinear thing. Yeah, a question?
A question to the ghost, because we last lecture we said that the ghost must be a scalar fields, but you also said that they have to be fermion fields, and I don't see.
Yeah. So the last lecture I said the ghosts have to be scalar and fermion, which sounds like a total contradiction. Well, there's no contradiction, right? We can have spinless fermions in the non-relativistic world. That's totally fine. The contradiction, if there is one, is with the PCT theorem, which says that spin should be connected to statistics. However, that of course only relies on physical, on fields that correspond to physical objects. Ghosts are imaginary objects that should cancel by the end of the derivation. So they're allowed to break the rules. There's no, the PCT theorem does not apply directly to the ghost fields.
But how can you say that this are fermion fields if they could be anything?
How can we say they're fermion fields if they could be anything? Well, they're definitely fermion fields because they're Grassmann numbers.
Okay.
So they're definitely obeying this statistics here, right? So we introduced them as auxiliary Grassmann numbers. I guess fermion was maybe, classical fermion. This is all the classic. This part, this step here is still a classical computation. So I should have, yeah. I guess I didn't stress that enough. These ghosts at this stage are classical Grassmann fields. Yeah, I started calling them fermions, perhaps a little prematurely. This trick here, where you get determinants from functional integrals, that works for functional integrals over Grassmann fields, not over fermion fields. So that confusion, if every time you see a classical quantity and I say fermion, you should be thinking Grassmann number, if I make this mistake again. Okay. So now we fix the gauge and we end up with an expression that's astonishing. I think it's really remarkable. We take this horrible nonlinear looking thing here and we end up with, after all these steps, something that looks like a path integral of e to the is, where s is again a local action. And so that is a pretty impressive thing to have happened. Because what it allows us to do is interpret this new gauge fixed path integral as a path integral, just a normal naive path integral. So that's what we get after all these derivations. So I'll write out the effective Lagrangian that we get out of all of this. Your question? Shouldn't this be the covariant derivative? Is the question. It is the covariant derivative. I've just taken all the terms which depend on G into this interaction part here. Now, I'll just leave that. I won't bother writing out many more details. You can look at the previous lecture to see the Lagrangian with the covariant derivative. So the point here is that we have now got if you looked at this, if you were just presented with this as a homework problem without any context, you would already have some sense of how to do this path integral here. You have some Lagrange density, which is quadratic. You know what to do with each of these terms. Even this term here, right, is a familiar looking term. Plus some stuff that depends on this constant G, and that's, you just look at that and call those interaction terms. So what do? Well, you substitute in L naught into the path integral. You substitute L int into the path integral, and you do a Taylor series in the smallness of G, because that's the only technique that you have at the current time to calculate any of these things here. And although G in applications is not small, there are regimes where it can be effectively small. Fortunately, we won't have time, I think, in this course to talk about that. So if you just looked at this, if you forgot all the context of how it came here, you'd just say, okay, well, I've got some very peculiar but possible to do path integral. And you would probably not question too heavily the origin of it, because it's on a homework sheet, and you just start calculating, right? And what would you get? Well, you'd get a Taylor series, right? When you substitute in this and you expand in the smallness of G, you just run the techniques that you've been taught on how to do path integrals over bosonic fields, how to do path integrals over fermionic fields, and also, well, you'd be a bit surprised, but you would do a path integral over this Grassmann field here, and you'd get some numbers in the Taylor series. So what do you get at the end of all this? You get Feynman rules for the transition amplitudes of the theory. You get Feynman rules for how an A boson can scatter off another A boson. You'd get rules for and results for how an A boson scatters off a psi boson, and so on. I'm going to write out the Feynman rules for this perfectly ordinary looking path integral. And then we'll discuss some of the big questions that I mentioned in the previous lecture. So remember, the name of the game here isn't to use this, is not to make a perfect derivation, but rather to find the right guess for a quantum theory. And we suppose that the theory defined perturbatively by evaluating star, where star is this path integral, our working conjecture now is that that theory is a quantum theory. So I'll tell you how to calculate processes in this theory, and then we'll talk about how it defines a quantum theory after that. All right. So you begin the tedious work of expanding this path integral in powers of g. And at zeroth order, you only encounter propagators. And you roughly know how to deal with those already. Remember, we have two types of, two labels on our fermion fields now, because our fermions are actually doublets of Dirac fermions. So we have two labels. So you encounter, first of all, propagators. A propagator for the fermion field. There's lots of fermions, right? Alpha runs from 0 to 3, and J runs from 0 to 1, or 1 to 2. Doublet of these fermions. And then, what else do we have? Well, we have also these boson fields. They're just perfectly ordinary bosons as far as we're concerned. With a mass, they have an effective mass, these bosons. Well, sort of. If you look at this extra term there with the psi, it looks like a kind of mass term. And when you work this out, you very quickly decide that the propagator for the A fields has this particular form. Okay, so you have lots of components to these A fields. There's three. The index A runs from 1 to 3, and the index mu runs from 0 to 3. So there's 12 objects here. And finally, you have this, as you work out the Taylor series, you encounter the C. You don't have any intuition for the C, but you sure know how to calculate the integrals. And you attach the following propagator to the C's. If you don't question things too much, you would imagine that these C's come from fermion fields which have this propagator here. There's 3 C's because A runs from 1 to 3. So that's the first thing that starts happening when you start writing down the Taylor series for this path integral. And I'll put hats over everything here. So whether you like it or not, you're forced to admit the existence of some spinless fermion fields, C hat, which aren't precluded by the PCT theorem at this point. Yeah, a question?
Sorry, for the bosons, the property of the bosons, is this G minus the other stuff, or is it G times minus the...
Oh, yeah, that's a good question. Is in this expression here, is that G all divided by K squared? No. Oh, I know why it's not, because I made a mistake. Ciao. That's correct in the brackets. But I'm missing a term here.
What's correct? Is this a difference or is it a product?
That's a difference.
It's a difference.
That's a difference. And what I'm missing is the K squared plus I epsilon on the bottom here, which is why it looks like it should have been a product, because you were expecting the one on K squared. Good. So that I think is correct. Yep. All right. Now that's for, this all comes from the G equals naught part. And then as you expand in powers of G, of course, you encounter interactions. You encounter integrals which involve products of propagators and additional contributions from the actual interaction terms in L int.
One question. Do we need an arrow for the C amplitude?
The question is, do we need an arrow for the C amplitude? In this case, not. Oh, yeah. In momentum space, you need the arrow, definitely. Right. Now, let's deal with the vertices. These are the what... as you expand this thing in a Taylor series, you encounter more and more integrals. And you could just do the integrals in a Feynman diagram expansion by just doing the integrals without noticing any patterns. Or you could make your life a little bit easier by noticing patterns and quantifying them in terms of diagrams, which is what we definitely advocate in this course. And so the vertices, there are several ways that these terms can interact with each other. There's a way for fermions to interact with the gauge bosons, giving a contribution that looks like this. G is slightly unfortunate. I will change this G here, which is the metric, because I don't like that it's interfering with this G here. So we're going to just put eta there for this part of the lecture. That's just the metric there. Yeah.
So T is the generator of the Lie algebra?
Oh, T are the sigma matrices, sorry, divided by 2. Okay, so that term, this term definitely appears when you start doing the Taylor expansion of this L int, and that comes from the covariant derivative inside the fermion part here. So that interaction there comes from the covariant derivative part in that, in the fermion part of the Lagrange density. Now we have another vertex. There's a way for, oops, I went too quickly. There's a way for a 3 gauge bosons to interact.
Sorry?
Yep.
In which direction looks the fermion first picture? The boson. Thanks.
Yeah, I believe that's correct. So we get a process, or we get integrals where we have 3 boson fields, and these have the following eta. So we get processes or integrals which involve 3 boson fields, and those we associate with coefficient 2. And we get also more processes. We also get integrals involving 4 boson fields, because this comes from the curvature term in the Lagrange density. The commutator of the covariant derivative with itself has cubic and quartic terms when you square it. And it gets sort of successively more complicated. You get a process involving 4 gauge bosons, and we're not done yet.
Sorry, but in the second part, do you use an imaginary unit? Like in the case above, there's no I.
There's an I here?
Above.
There's no I, that's correct.
That's correct.
Yeah, because if you look in the covariant derivative, there's I's and not I's at various places, and if you have 3 of them, then the I's cancel, but if you have 4, then they don't cancel. So Good. There are still yet more processes. Well, this is, in fact, what I've got on the board here, apart from this ghost bit here. If you ignore the ghosts, you have what looks to be a quantum theory of fermions and bosons, right? And that's the gauge fixed part of a nonabelian gauge theory. It defines this sort of sub-theory where you only draw wiggly lines and straight lines. There's no reason to think that'll give you a healthy theory, but it's certainly a sub-theory here. All right, there's one more vertex. This comes from the covariant derivative term involving the ghost field. And we associate to this process here, this quantity, P mu, that should be a P. All right. That's it. So after a lot of, this is, if you like, a gigantic exercise, is to go from the Lagrange density that we derive for the gauge fixed nonabelian gauge theory, do the Taylor series, and then work out these Feynman rules for all the terms in the Taylor series expansion, plus symmetry factors. I'm not going to write out all the Feynman rules in all their glory. I've written out the important ones here. The rest to do with symmetry factors and signs and so on. That's for you to and conservation of momentum, right? That's what the etc. is. That's for you to work out. There's nothing new there. There's no, this theory doesn't present any new features. All right, so I've very suggestively written for these propagators hats as though these things define quantum processes. And that brings us, of course, slowly and surely to the big question, one of the big questions. we have a theory of integrals, we have a theory of Taylor series. So we're doing, when we have this path integral prescription, and I've suggestively written things with hats on them. And so the question is that if you start putting hats on quantities, does this prescription here, where you attach to this process here, this number there, does it actually define a quantum theory? So how could it not? I guess it's worth sort of saying, how could it not define a quantum theory? Well, it would not define a quantum theory if waiting for t seconds, if propagating in time was not unitary. That's one way it could fail to give us a quantum theory, is that when you work out at the level of perturbation theory a process for, say, waiting t seconds of time, that wasn't unitary, that probability wasn't conserved. That would be a sure sign that this doesn't define a quantum theory. There's other more subtle ways in which it could fail. It could actually give you something that resembles a quantum theory. So you could find that any process that you were interested in appeared to come from a Hilbert space built from sort of like applying C's, A's, and psi's to some vector, but you might find negative norm states. So the second failure mode, the first failure mode, well, that's pretty catastrophic, and it shows up pretty quickly when you look at symmetries of the correlation functions. Do the correlation functions, are they symmetric under the Poincare group? If they are, then you're more or less satisfied that it's at least, you're more or less satisfied that probability is conserved in the right way. You still don't know if this is coming from a quantum theory, though. So then, suppose you check that, right, and you get a tick. Oops. Well, whatever. Tick is sort of ambiguous in this context here. Suppose you check this first failure mode and you decide that it's not failing, so it's a good theory up to this stage. Then there's yet another way it could fail. You could define operators on a linear vector space. These things, this theory could end up defining these C's, A's, and psi's as operators or as distribution valued objects. But you could get negative norm states, which is to say you build a Fock space of states, but that the inner product that you end up implicitly defining isn't positive definite. That's another way to fail. It's another way that this theory could fail to give you a quantum theory. Interestingly, this isn't quite a failure. And this is where we really are at the cliff face of current research here. If you have an inner product which isn't positive definite, then that's not a Hilbert space. We're done, right? There's no sense in which what you're getting is a quantum theory. Your state space is just not a Hilbert space. But it could be, and it is the case, that the inner product between physical states is positive for all phi's, and that there is a subsector of this linear space which has negative norm states. That is exactly what happens in this case. Now that actually is not in contradiction with this being a quantum theory, because you can mod out by those states, these negative norm states, to get an effective quantum theory of the physical states. So to be a quantum theory, this is actually a bit too restrictive, this condition here. All you want, and all you really need, is that operationally defined quantities have positive inner product like this. Or if you like, that the state space of your theory, the space of physical states, that's a convex cone that comes from an operator algebra. It's a very fancy way of saying that. And that's indeed the case here. I won't really be able to get into this in this course. That requires quite a lot more detailed derivations involving these and studying these processes explicitly. I will just signal that this is a failure that you have to be worried about, and you have to check that that for physical states, the norms are always greater than 0. That is a way out of that. You'll still get an honest quantum theory in the background that way. Now you can answer these questions by looking at correlation functions, and these correlation functions are in turn defined by power series and Taylor's expansion of the Lagrange density and the action. So that's sort of one big question. Can we interpret this theory as a quantum theory? And at the end of the day, the answer is yes. It is a quantum theory. That's a whole chapter of a book, if you like, and one that we're not going to study any further. All right, the next thing, there's another big question. Okay, it's a quantum theory. Well, of course, I must be lying to you in some sense, because surely some of these diagrams are going to evaluate to infinity. So I must have been cutting them off in trying to answer this question here. And that's indeed the case. So all of this is subject to a cutoff, of course. Therefore, that leads into the next big question. Which is this theory renormalizable? Is it possible to add counterterms, or is it possible to shift the coupling constants so as to absorb the effect of changing the cutoff, which is another way of saying, can I make my predictions for physical processes at low energies independent of the cutoff? The answer is yes. So this is a result of 't Hooft and Feldman, a tour de force in quantum field theory. It's really one of the kind of high points in the history of high energy physics, is the proof of a 't Hooft and Feldman that this theory, so defined, is renormalizable. Is it renormalizable? The answer is yes. I'm not going to be able to go through that proof in this course, but I'm going to give you a sense of some of the tools that they developed to prove this result. And I guess, you know, apart from the hard combinatorics required to prove this, there's some really quite elegant tricks that were developed and are extremely useful in more general contexts for dealing with processes defined by this path integral. And I want to dwell on this for a little and tell you about the cutoff that they employed to prove that this theory is renormalizable. This is a very interesting result. So remember in our discussion of renormalization theory, there's an infinite way of putting cutoffs on a theory. Right? We're allowed to, when we don't put a cutoff on a theory, we're making a hypothesis which is far too strong about how the elements of reality behave. When we put a cutoff on, we're just saying we're admitting our ignorance about how the theory behaves at high momenta or for degrees of freedom we cannot observe. Therefore, a cutoff is just a way of admitting our ignorance. There's various different ways to admit our ignorance. We could cut off in momentum space and say that we don't know what's going on in momentum space. We can cut off in position space and prevent things from having too fine a resolution, and so on. And depending on the cutoff that you use, you preserve various features. You make various statements about what you believe to be true about reality. So a cutoff is a way cutoff is a way to admit our ignorance, right? And not all cutoffs are born equal. Some cutoffs make stronger hypotheses about how reality behaves. Now, one cutoff, one hypothesis that we have about reality that we have very strongly is that nature is Lorentz invariant. So at this level of perturbative quantum field theory, there's a strong belief that that physics is Lorentz invariant, Poincare covariant physics. And when you put in a sharp momentum cutoff, what's happening is you're breaking you're explicitly breaking that symmetry. So the process is all your calculations can no longer give you manifest Lorentz invariance anymore. That's impossible. If you put in a cutoff that breaks Lorentz invariance, then everything you calculate will no longer be Lorentz invariant, and then you may end up defining a theory which is renormalizable, but the difficulty you have in later showing that theory gives rise is coming from some Poincare invariant theory is much harder if you put a hard cutoff. So that's at least one motivation to think a bit harder about cutoffs. Maybe it's possible to find a cutoff where where all the processes are at least manifestly Lorentz invariant. Another invariance that gets wrecked by the momentum cutoff is gauge invariance. So admittedly, we fixed gauge invariance in this theory that we've been looking at in the past two lectures. But you hope that invariance will be present in the quantum theory, and if you put in a cutoff that's too stupid that wrecks that invariance, then you're going to have to work presumably harder to show that the quantum theory does inherit that invariance. So this motivated 't Hooft and Feldman to think very hard about what kind of cutoff would be best and most compatible with Lorentz invariance and gauge invariance. And they came up with one. It's a very elegant proposal. They came up with a cutoff called dimensional regularization. So that's what I want to discuss, I guess, for the rest of this lecture before we get on to lattice gauge theory in the sequel. So dimensional regularization, what is it? Well, it's a way of rendering the integrals in a Feynman diagram expansion finite, okay? Obviously, it must be, right? Because we're taking the theory that's divergent and we're going to replace it with a cutoff theory, which is not divergent, which does depend on some kind of cutoff. So to discuss this, I guess I'm going to take an example and then show you how to implement dimensional regularization on that example. And then, after that, you should be able to generalize from that example to far more variety of different situations. Okay. So in 5-4 theory, this is an example of a theory in desperate need of renormalization. But also in like all the other theories we're going to encounter, we encounter integrals loop integrals which diverge. Okay, and that's a sure signal that we've made a too strong hypothesis about how the degrees of freedom of our theory behave. And the typical kind of integral that you encounter has this form here, and I'll explain this in a second. No, it's really an M here. Okay. So this is the kind of integral you encounter when you do the Feynman diagram expansion. This is a loop integral. N is an integer. And that basically tells you how many undetermined momenta there are. And then what's D here? D is the dimension. So up to now, the dimension's always been 4 in all of our discussions, or 3 + 1 Minkowski. But in this discussion, especially in this discussion, we want to allow the dimension to be, not specified. So it could be 2, or it could be 1. And then let's look at this integral just for a little bit already, and we're going to see some interesting features, right? So this integral, how does it diverge? Well, sort of the naive divergence assessment of this integral, well, we're going to get sort of like lambda to the power d from the integral part here. So when we stick a cutoff on this, you get, this is the good part, right? This is the bad part, sorry. Every power here creates a divergence. So you get lambda to the d. And the loop here, the loopy stuff, that gives us contributions that scale as 1 on lambda to the 2n, roughly speaking. So something that you notice sort of straight away is that in low enough dimensions, we don't have any problems at all, right? So what happens when we live in a 2-dimensional space-time? Well, life is good. 2 divided by 2 is 1. So a two-dimensional universe is a very nice place to live indeed. These processes don't diverge at all. In a three-dimensional space-time, the one-loop term does in fact diverge, right? But as soon as n is higher than 1, we're good, right? And so on. And so the story here is the lower you go, the lower the dimension, the less painful these kind of divergences are. And that, there's this sort of element of this in string theory where the whole theory is defined in a 1 + 1 dimensional surface of a 1 + 1 dimensional string. So there's sort of a shadow over this already there. So the difficulty is then with the fact that D is wrong. We should be in a two-dimensional space-time to make everything finite. We wouldn't even have to worry about this discussion over normalizability, but we're in 4. Well, what I'm going to do is just process this integral a bit. We're just going to make it a little bit nicer for this dimensional regularization recipe. So step 1 is to rotate the contour. So we got an integral over 4 variables. So we're going to separate this integral into 2 bits. We're going to separate it into the bit over time and the bit over the rest. And the bit over time looks like this. And the bit over the rest looks like that. Right? Done not very much in particular. And then we notice that, okay, this looks very much like the kind of integral we'd want to deal with using complex variable techniques. We have poles. At 2 places. Yeah.
Why do we have k to the power 3?
Where did I put the k to the power 3? Oh, sorry. The question was, why is there a k to the 3? Well, there isn't. There's a k to the 2. Better. Right, we got some poles, but otherwise it's a perfectly ordinary looking contour integral. I've done some Taylor expansion there. So as long as we avoid those poles, we should be able to move that contour around to make this integral a bit nicer. So in the k0 plane, so this is imaginary k0, this is real K naught, we have a pole sort of here. Oops, other way side. There's a pole here. There's a pole here. And this integral runs from minus infinity to infinity. So here's the contour that we're integrating over. But of course, we're free to use Cauchy's theorem, so we can rotate this contour and use the fact that when we close the contour we get 0 because there's no poles enclosed, and instead run the integral this way. So rotating the contour like this is an extremely useful device for this particular integral, and the reason is that if you look at this integral here, it kind of looks like that's k squared, right? The radius of some object in a high-dimensional sphere, except there's this irritating minus sign here, so we want to get rid of that minus sign. So all of this contour rotation amounts to just changing variable from k naught to I times k naught. And everything inside this region here is perfectly analytic, and so it's all meromorphic, so we're fine. We can rotate the contour like that. And after that, we end up with the result that this is minus I d to the d minus 1 k and we'll call this ke, not k naught, call it ke.
One question.
Yep.
Why do we have a pole at k small?
I Taylor expanded the I epsilon out of the square root.
Okay, and then okay.
After all that, we end with something quite simple. We end with an integral over k minus d minus 1 spatial normal spatial type momenta and one temporal component here of an integrand that looks like that. The I epsilon goes away, right? Yep, a question?
Where are the spatial parts of the momentum in the integral now?
Where are the spatial parts of the integral?
In the new integral.
In the new integral. So this is...
There's only ke, no k. And also there are 2 dk.
Sorry, that was this omega. There.
And you doubled the dke in the integral.
I doubled the dke in the integral. Did I? Oh, I did too, didn't I? Sorry about that. All right, hopefully that resolves all the difficulties. So when you do the Feynman diagram expansion for just about any relativistic theory, you always end up with these terms. More or less, there's often extra momentum hanging around. And then you can do this rotation here of the contour because the poles are always lying off the real axis here, and you can always rotate that way. And you end up with this integral here, which is a much nicer object indeed. Because now it looks like a spherically symmetric integral. So this Euclid here means that we can interpret that as just a normal Euclidean integral over a Euclidean momenta, right? All the negative part of the metric vanishes, and we're left with just this rather more spherically symmetric looking integral. And then, of course, there's a reason why we do this, and that is so that we can exploit that spherical symmetry to do this integral. So we do that next. You're not going to like this notation, are you? So we go to spherical polar coordinates, where we have this radius of the momentum vector, L equals the length of the K. And the integral looks like this. Okay, which is great, right? We can do d minus 1 integrals straight out. Oh, this is the surface of sphere. So we can do this integral super quick because, or at least we can reduce it to quadratures, because we can do that integral. Well, it's a little exercise. There's, fairly elegant ways of deriving this result. Which I'll leave you to discover. By doing some Googling. So the surface integral there is just the surface of the d-dimensional sphere. There's going to be some pi's in there. What's this thing? This is the gamma function. And that will turn out to be an interesting observation. Oops, I've forgotten an n, haven't I? Let's put that n back. So this won't be the first time we see a gamma function in this discussion. Good. So we've got to the point where we've reduced our problem to quadratures. That means an integral over a single variable, which you can evaluate, you know, by Simpson's rule on a computer or something. There's no further trickery needed to actually evaluate that integral. Of course, it diverges. I mean, you just have to look at it to see that that integral is diverging for d is 3 and 4. That's what we got right now. Now, we could just put it on a computer and study that integral, but it turns out, of course, that, you know, we're doing this work for a reason, and that is because we're going to find a clever substitution to do this integral. And almost the naivest substitution works.
Sorry.
There's a minus I missing, yeah?
Where do we get the 4 pi?
Where do we get the 4 pi?
Not the 2 pi.
Where indeed do we get the 4 pi? Yeah, I only make it to be a 2. Good.
We insert this integral first, do we? Or?
Yeah, of course, but do we get the 1 of the square root of 2 to the power of d from the substitution you do?
Yeah, yeah. So there's nothing magical here, what I've done.
I think the 4 may be right if you do this substitution, maybe.
Oh, but I haven't done the substitution yet.
Oh, okay.
I'm about to do the substitution.
Oh, sorry.
Yeah. So that's why I'm pretty sure it's a 2. All right, but if you do make the clever substitution, which is not that clever, I mean, look, you know, you want to get rid of this, so just whatever, define it like that. Then the integral becomes integral becomes that. Now, if you come from these days, I guess you would just go online and find some website that tells you what integral that is. In fact, I believe Wolfram has a integrator website. So you just type in the integrand and it gives you the definite and indefinite integrals. But in my day, you had a book, and that book was called Gradstein and Rizik. And that book is this thick, and you look through the book. And the book it takes you some time to look through the book, but eventually you find in its 1,000 pages or so that this is not just any old integral. This is actually a beta function. It's a rather special kind of integral, and beta functions are defined in terms of gamma functions. So let's write it all out. So I'm going to not bother with writing out the beta function. I'll just write out what it is in terms of the gamma functions. And remember that gamma functions have this nice factorial-like property, indeed the generalization of the factorial function. So when you encounter gamma n minus d over 2 times gamma d over 2, you can simplify that somewhat. No. You just cancel. What am I talking about? There. All right, now we can see the explicit divergence of this integral. Exactly see where it's going wrong. Right? And it goes wrong because gamma has poles. So the divergence is coming from the poles of this function here. But gamma is a very nice function as long as you're not on a negative integer. So n is, we're stuck with n. N is given to us by the Feynman diagram expansion. But d is like this one number that's fixed from the outset of all our calculations, and that's the dimension. We usually substitute d as 4. But what if d is not an integer? Well, then it's perfectly finite. So this is the idea behind dimensional regularization. The idea is to regard d as a parameter in the Feynman diagram expansion, akin to a cutoff. Now, it has no operational meaning to talk about d not being an integer. But that doesn't matter, because at the point where you have a Taylor series of integrals, which depend on the parameter d, and you shift d slightly, I mean, everything depends nicely on d, then you just think of that as a kind of hypothesis that you're making, or a cutoff. So the trick of dimensional regularization is to say, let d be 4 minus epsilon, where epsilon is greater than 0. And then study how this diverges as epsilon goes to 0. So it's a mathematical trick that cuts off all the divergent quantities into finite quantities which depend on epsilon. We knew that was going to happen. But the very beautiful thing about the dimensional regularization is it doesn't break any symmetries like Poincare invariance. Because all the terms still are expressly Lorentz covariant. And now we can look at how one of these integrals diverges. Let's just take an example.
One question.
Yeah.
At the point we started, we could have chosen n equals 1, and then we would have a divergence. And at this point, we don't have a divergence at n equals 1, right?
So the question is, we could have chosen n as 1 and we would have had a divergence, but now we do not have a divergence at n equals 1. Is that correct? Is that the question?
Yeah.
Yeah. It also diverges for n is 1. I didn't write that down. So we got a ratio of gamma functions here. So we so if d is 4, then that's 2, and n is 1, then we've got gamma of minus 1 in there. So that's bad. So let's do an example of gamma 2 with this 4 minus epsilon trick. What's going to happen? Well, okay, if you work it all out, I believe we should get this. So we get gamma of 2 minus 2 plus epsilon over 2 divided by gamma of 2. Gamma of 2 is, of course, 1. How does this behave? Well, it's got a pole at gamma is 0, at n is 0. So, but it's not at 0, right? It's at epsilon over 2, so it's a little bit away from the pole. So this is a nice bit of good complex analysis or special function theory. And we see that loop integral diverges, of course, as epsilon goes to 0. That's definitely was to be expected. We get this additional constant here, the Euler-Mascheroni constant that comes from CH, I believe. And we get some stuff which behaves quite nicely as epsilon goes to 0. So the bad bit is here. So if you compare this prototype integral here with one that you've actually looked at, then we can interpret what does epsilon mean, what kind of cutoff is epsilon. So if you compare with this cutoff at momentum is lambda, then you see that epsilon, 1 on epsilon should be compared with lambda. So the cutoff here is 1 on epsilon. The smaller epsilon is, then it's analogous to having a momentum cutoff around lambda. Of course, it's not exactly the same because in the dimensional regularization, we don't put a hard cutoff on momentum. But you should think of epsilon as being comparable with the cutoff that comes from the hard cutoff. And now you can do, now you've rendered every term in your Feynman diagram expansion finite, yet it depends on epsilon. And then you have to play the game of adding counter terms to the Lagrangian so that you can adjust the coupling constants to absorb that epsilon dependence. Now that, of course, is the topic of renormalization, and this is a Torfman-Peltmann's contribution. We won't be able to go into that in this course. A question?
Yeah, I get that we can, or that we are able to renormalize the mass or the charge, but I don't get how we are possible to renormalize the dimension. Like
okay, so the question is, how are we renormalizing dimension? We're not renormalizing dimension. So d is a parameter in these integrals. That's what I stress again, that d here is not the dimension of space-time. We're not changing the dimension of space-time here. We're changing the integrals that are in this Taylor series that we have to calculate. And we're changing them by adding a free parameter. In this case, the free parameter is epsilon. And this is, at the surface, no different from what we did here for this integral here. We had an integral that we had to do. It diverged. And we put on a hard cutoff at momentum lambda. Another way of saying it is that we made that integral depend on a free parameter lambda. And that that hypothesis corresponded operationally to saying that there are no processes involving momenta above lambda. That was easy to interpret, right? Because we could see that we stopped k going above lambda. In dimensional regularization, it's much, much harder to understand what does it mean when we are introducing this parameter here and cutting off the integrals. What's the operational interpretation of that? And to be honest, I have no idea. Multiple people have asked me that question, and I've asked multiple people the question. It's a kind of soft cutoff in momentum is the best answer I can give you, operationally. A very clever soft cutoff in momentum. But it's, in Hamiltonian terms, it's very hard to translate what this thing is doing. So I stress it's not an operational thing. It's a way of cutting off divergent integrals by introducing a free parameter, kind of like in a Legendre transform. You trade degrees of freedom for Lagrange multipliers. And then you have to get rid of it at the end, right? That's our big task. So I'll talk about that a bit in the next lecture, I guess. But for now, I think we can stop here. Thank you.